RenderFormer v2, Neural Rendering with Heterogeneous Scene Primitives. A pre-trained transformer that turns a sequence of mixed scene primitives into an image with full global illumination, with no per-scene training and no handwritten light transport code. RenderFormer v1 showed that global illumination can be learned as a sequence-to-sequence transformation. A scene becomes a sequence of triangle tokens. Camera rays become query tokens. A transformer maps one to the other, and the image comes out with no ray tracing and no per-scene optimization. But V1 is a proof of concept. Triangles only. A fixed GGX reflectance model. Full attention, so under 4,000 triangles at 512 by 512. Real scenes are bigger than that, and they are made of more than triangles. V2 keeps RenderFormer V1's two-stage structure. A view-independent stage that resolves transport between primitives, and a view-dependent stage that turns ray bundles into pixels. However, V2 differs in three key areas. First, the sequence is now heterogeneous. Triangles carry vertices, normals, and a material code. Voxel media carry a 4-cubed scattering grid. Lights get their own tokens, not fused into geometry. Environment maps enter as two sets of latents. And camera ray bundles, one per patch of the image. All 5 kinds share one positional encoding. Rotary positional encoding, applied to the primitive centroid rather than to its place in the sequence, ensures the embedding is translation invariant. This has the advantage that a new type of token does not need a specialized positional encoding. Second, materials. V2 has no hard-coded reflectance model. Instead, appearance is embedded. We render a sphere under a fixed light probe, encode it with a CNN into a 9-dimensional code, and add that code straight into the primitive token. The code is never explicitly decoded. RenderFormer v2 learns to evaluate the reflectance directly from that code. Because the space is defined by rendered appearance rather than by parameters, any BRDF model works, including measured ones the model never saw in training. Third, render-aware sparse attention, designed to scale the model to larger and more complex scenes. Nearby primitives dominate light transport, so we sort the primitives along a Hilbert curve. Neighbors in space become neighbors in the sequence, and a one-dimensional sliding window of plus or minus 256 keys buys us a spatial one. But light transport also contains non-local components. So we add an attention sink that every token always attends to, and that attends back to every token. It holds 3 things. 16 registers, free scratch space for whatever is globally true of the scene. Every light source, so each primitive sees every light, whatever the distance, the attention analog of important sampling the lights. And one mean pooled summary per 64 primitives, which keeps long-range occlusion in reach coarsely. Quadratic attention becomes near linear, and it is not only cheaper, it is better. At 83,000 triangles, dense attention loses focus and darkens the scene, while the sink keeps the highlight and the contact shadow. One set of weights renders all of this. Refraction, environment lighting, volumetric scattering, textures, displacement, and scenes with a large number of primitives. There is no effect-specific code path. Each effect is learned by example. Nothing in the loss asks for temporal coherence, and every frame here is an independent forward pass, but the results stay stable as the camera, the lighting, and the materials move. Against V1, at 128,000 primitives, 9.9 decibels more PSNR and 4.8 times lower LPIPs, which is the point where V1 has essentially broken down. Cycles takes about 5 seconds a frame here, and V1 4 with full attention at this scale, while V2 takes 3.5 times faster at up to 2048 by 2048 with no upsampling. The ablations agree. Dropping the attention sink costs nearly a decibel, dropping the sliding window 1.3, dropping the light tokens a little less, dropping the summary tokens a little more, and sparse attention beats full attention while computing far less. Training is 10 million procedurally generated scenes, about 70 terabytes, all rendered offline with cycles, in a 5-stage curriculum that grows resolution and primitive count together. 19 days on 32 A100s, and after that, no fine-tuning to render a new scene. Limitations. At most 8 light sources from the training data. No explicit temporal coherence, and none in the loss. A fixed 32 by 32 texture on every primitive. And a new primitive type means retraining. Paper, code, the pre-trained model, and the full gallery are at renderformer.github.io/v2. Thanks for watching.